Hello, welcome to this new video where we discuss mathematics and physics. Today what we are going to discuss is basically the classical Doppler effect when we talk about sound waves, for example, propagating in a medium, or other kinds of waves propagating in a medium. So that's what we are going to do today. Right, okay, so let's put things a little bit in context here. So what we are going to consider is a point source here, S, that is sending off a signal in the form of a wave, but in principle that can be any kind of signal with a sort of so-called harmonic signal with a periodicity to it. And this particular signal is being received by a receiver that I call here R with a particular at a particular location here, which is X. Okay. And the thing is that well, which is XR in fact, notation wise. And the thing here is that the receiver is moving at velocity vr, for example, and the source S is moving at velocity vs. And the question we want to ask is, what is the difference between the frequency of the signal being actually sent out by the source as opposed to that of the signal being received by the receiver? Okay, and the fact that these things are in motion is going to play a role. Now, one important point here is that when we mention these velocities, Vr and Vs, we need to say relative to what, right? Because when we talk about mechanics, then we know that that the laws of mechanics only work in inertial frames, and then we want to know what kind of frame we're talking about, and that is relevant to depicting the propagation of a wave. By the way, here, the wave is characterized simply by this wave front that I've kind of drawn to represent the wave that will be moving kind of away. But again, these kind of patterns could also be sometimes people do it with like balls that are being sent by the source and then being received, so some kind of packets or something. So it doesn't matter really. But so that's the idea. So that's kind of the wave or signal being sent out. That's the source, and that's the basically the receiver. So what is the actual frame of observation relative to which we call Vr and Vs for the velocities in 1D? So here I'm going to focus in 1D. Well, this is basically the frame. So that's all of that is relative to the frame where the medium is at rest, if it's a wave propagating in a medium. Okay, so that's kind of the idea, and then you have a corresponding wave in that corresponding, let's say, phase velocity relative to that. Okay, now in that particular picture and in this particular frame, we look at things really passively, and what we want to describe, like, this particular, if it's a wave, and I'm going to focus kind of on a wave, if it's a wave, then this is going to follow the wave equation. Okay, I'm not going to go into details about what the wave equation looks like. That's not kind of the point of this today. But basically it's going to follow the wave equation, and in particular it's going to have a solution which is that of a wave, and that's the most important part. And the general kind of equation for a wave is going to be something like this. So you're going to have, let's denote, I'm not too sure exactly how to denote that. Yeah, let's denote f, so that's a wave that I have the signal or whatever, and that's a function of t and x, and that's going to be equal to some amplitude f0 and then cosine of some omega t minus kx. Okay, now these different things, these things correspond to different quantities. So the omega here is the so-called angular frequency, or sometimes simply frequency, but we need, if that's the case, we need to be careful that this is a frequency expressed in radian per second. And then this other term here is k, and that's called the wave kind of vector. Okay, or sometimes wave number. Okay, so basically that's a general form of a wave. In principle, you may have actually some extra phase shift here if you want, but I've basically absorbed that phase shift into F0, and basically my definition of t equals 0. So that's kind of the bottom line, is also to make things a bit simpler. So now what I'm going to do is that this is actually depicting again the wave itself, okay, the signal itself, when I'm looking at it from a frame where I can actually describe it, okay? So that's the case. And this is completely independent of the notion of source and the notion of receiver. So the reason why I say that is because what we can do is basically, here this is for any x along that line. And what I can do is basically say, oh, what if I were to follow some x, which is the position, the successive positions over time of the source or the receiver. Okay, so here x again is to be interpreted as a set of values that I can look at any given time. So x and t here are supposed to be independent of each other. But then I can say, what happens if I follow along a particular point in space, okay? And I can follow the receiver or the emitter, and then, or the source, and then we'll see what basically comes out of it. So let's start by the source, okay? So let's assume that the source has this particular form. So we've got x, and we've got, let's say, xs of t, and that's going to be vs times t. And let's say that there is no x0. This is just x0 equals 0. So basically at t equals 0, the source is at 0, just for convenience. So if I actually substitute that into there, I've got actually only a function of time now. So I've got f of t and then x s of t. So it's only a function of time now, and that's going to be equal to f0 and then cosine and then omega t minus k, and then I've got vs t. Okay, now if I actually factorize these things, I get that this is cosine, and I factorize by omega, and then I get that this is I factorize by omega t. Let's do it this way. So omega t, and then I've got 1 minus k over omega, then vs, up, and like this, okay? But that's the crucial thing. If I'm actually following the source, okay? If I'm the wave and I'm exactly looking at that wave at the source, then it must be equal to the generating signal itself that is generated at a frequency omega s. And so it has to be, that's by definition, it has to be equal to omega s times t. Okay? So by comparison between this equation, which is like the emitting kind of source material, frequency and so on, and then what I'm observing if I follow along this particular wave equation and following the source, then I get that omega s is equal to omega times 1 minus k over omega vs. Now I can do the same with the receiver. So for the receiver, let's actually put the equation of motion here. So xr of t is going to be, for example, equal to VR of t, and then plus some x0. Again, I'm going to substitute in there, so I've got f of t, xr of t, and that's going to be equal, and I'm going to, basically I'm going to perform the very same calculation here, so it's going to be cosine, and I can readily write this part here, because that's the same I'm doing, so omega t, and then 1 minus k over omega, Vs, and then I've got Vr, sorry, and then I've got this plus x0. Okay, and because this is the related to the received frequency, then the receiver itself is simply just receiving stuff. Okay, so essentially what I have is that I can equate that to being f0, and then that's going to be cosine, and then omega r t. Okay, now the x0 here can actually be absorbed into like the time difference, right? So the time delay it would take to actually reach that point. So that's basically the way you can do it. So at the bottom, so at the end of the day, it kind of doesn't matter what this x0 is going to do here. So either you absorb it into your definition of t, or you can put that this is simply omega r t plus x0, for example. Okay, just to add this phase shift to the equation. And so what this is going to give you, therefore, is that omega r is equal to omega, and then 1 minus, and then Vr over, Vr, that's k over omega, then Vr, and basically that's it. Now, the final bit of this derivation is basically to say, hold on a second, but for solutions to the wave equation, okay, but for solution to so-called the wave equation, we have the following. We have that we call the celerity c. It's not the speed of light. That's what is called the celerity of the wave. That's basically the phase velocity is actually equal to omega over k. Okay, so omega over k is a constant. It does not depend on omega, at least for, again, a single kind of wave equation, which is a linear equation. Okay, so in that case, although here we factorize by omega, the ratio k over omega is independent of omega. Okay, so what we do, therefore, is that we put together, and I'm going to do it here because then it's going to complete the formula. I'm going to substitute here k over omega as 1 over c in both equations, and then we are going to get, therefore, that omega r over omega s is equal to the ratio of that, the ratio of that over that. Okay, and so that's 1 minus, and I've got Vr over c divided by 1 minus Vs over c. Okay, and basically that's it. That's your Doppler formula that actually accounts for both the velocities of the receiver and also the velocity of the source. So let's see how that goes. So let's say you're here, you're the receiver, and for example, the receiver doesn't move, okay? So the receiver has Vr equals 0, so that's going to be 0. If Vs is going that way, then it's telling you that the frequency being received is going to be larger than the frequency being basically not received. Likewise, if instead the source is going away from the receiver, So Vs would be negative, in which case you've got a plus sign here, and then you're going to see that the frequency received is actually larger, well, smaller, sorry, than the frequency being emitted. Okay, so that's how this Doppler formula works. That's how it kind of functions. You basically write something which is true in the medium itself to describe the wave, and then you actually follow along the receiver or the source that you then identify as being a single signal being perceived by the receiver or emitted by the emitter. Okay, so that's again what we've seen in these two equations here and here. Okay, so that's it. Now, of course, there are plenty of derivations of the Doppler formula when it comes to sound waves and waves in media, etc. Personally, I find this to be the easiest one because the strategy is the same for both points, and there is really this idea of following a particular point that has a particular equation of motion, which to me is very natural. But it could be that there are some others that you prefer and that are completely different in spirit. So I know actually of other ways of deriving these equations, but often they appear to me at least as more contrived. But if you know some that you like very much, please do let me know in the comment section. And you know, I really would like to know some other ways to actually get this Doppler formula. On that note, I tell you, you know, have a good day and see you in the next video.